Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
A very good afternoon, everyone who's gathered here in this virtual room from Banda Aceh, where this conference is supposed to be held. And a very good afternoon, a very good morning for the speakers away from us in Europe. Here we have already Dr. Morelia Urlaub. Very good morning for you and a very good welcome. I would like to introduce myself. My name is Ella Melianda, and today I am at this session. I'm the moderator for this keynote speech from Dr. Morelia Urlaub. A bit introducing myself. I am I am a lecturer in the Civil Engineering Department of Shah Kuala University, and also assistant professor in the same in engineering faculty, and also one of the researchers in the Tsunami and Disaster Mitigation Research Center of Shah Kuala University. I would like to now welcome Dr. Morelia Urlaub from Geomar, Germany. I understood you are currently at Kiel or in Germany, or yeah. So a very warm welcome for you. Thank you for your time to contribute to this very nice meeting we have. So I would first to introduce you. Dr. Morelia Urlaub is working in the dynamic of the ocean floor or marine geodynamics in Geomar, Germany. That is the Helmholtz Center for Ocean Research in Kiel, if I understood correctly. I would like to describe to the audience your scientific interests, which consist of submarine geohazards, long-term seafloor deformation monitoring, submarine landslides and slope stability, fluid flow in continental slopes, numerical modeling, and a little bit about the education and the career background of Dr. Urlaub. Until present, she is a research scientist in Geomar Helmholtz Center for Ocean Research in Kiel, and previously a postdoc in National Oceanography Center, Southampton, UK, and finished her PhD in 2012 in the University of Southampton, United Kingdom, Master of Science in Marine Geosciences in University of Bremen. That's where actually I spent 2.5 years back in 2010 to 2012 as a postdoc in Marum. If you must be familiar with this institute, very well-known institute.
Yes.
Yeah, so that's about the CV of Dr. Urlaub, and I would like to welcome her speech today as a keynote with the title Flank Instability of Coastal and Ocean Island Volcanoes, a Shoreline Crossing Process. We have, I think, the last session of today, so we can be a bit more relaxed and you have plenty of time to present your presentation, and hopefully all the audience still very enthusiastic in having discussion afterwards. So the time is yours. Thank you.
Yeah, thank you very much for the very nice introduction. And yeah, I think we probably must have just missed in Bremen because I left in 2009. So otherwise, I'm sure we would have met.
Yes.
Okay.
And I'm quite familiar with the Kiel Institute over there. So, please go ahead. Thank you.
Nice. Okay. So I hope you can see my screen now.
Yes, we can.
And okay. So yeah, thank you also very much for the invitation to give this keynote lecture. Yeah, so I guess it's already evening for you. And you must have had a long day of talks and lectures. So I hope I can make this a little bit easier with some nice pictures and hopefully interesting. So this talk will be mainly about marine research on volcano flank collapses. And I will be showing a whole lot of data from different new and old or well-known old established technologies. And with all of these, I would like to demonstrate how we can make the invisible, so everything that is covered by seawater, a bit more visible. And so I would like to start with a little bit with something onshore, actually. So in recent days, we've been seeing these dramatic pictures from the ongoing eruption at La Palma, so at Cumbre Vieja volcano. And just to give you a bit of a background, so this is Africa, and the Canary Islands are a series of hotspot volcanoes here off the west coast of Africa, and La Palma is the island to the northwesternmost island, and it is currently erupting, and it has been erupting for 1 week now, and a very big lava flow is currently on its way downhill towards the sea, and a lot of people have been evacuated, and more than 400 buildings have been destroyed. So there's a lot of interest for all European volcanologists at the moment on this volcano. So yeah, but if all the action is taking place here and above the seawater, why should we also care for the offshore? And I would like to take you to another volcano in Europe, and another active volcano. And this little guy here is Stromboli Volcano. And I just made visible what is actually visible to us, so what is above water. But as you may expect, this is by far not everything. So if I add the seafloor, the scene changes quite drastically. And so we can see that this volcano that actually looked quite small, it's not small, it's actually very big. And of course, it is also in the water where the biggest hazard is generated. And there are tsunamis that can be caused by landslides that result from the partial collapses of volcanoes. So a bit more than 2 years ago, the world witnessed such a chain of events in what must be very well known to you, the case of the eruption, collapse and tsunami of Anak Krakatau on the 22nd of December in 2018. So the collapse reduced the height of the island from a bit over 300 meters down to 110 meters. So this is, I think, very nicely visible on these two images here before the collapse and after the collapse. And the landslide caused a tsunami that affected all the surrounding shorelines. So here is an image showing the result of tsunami models. And we can see wave heights of up to 10 meters. And this event, I think, demonstrates how far-reaching consequences such flank collapses have on volcanoes that are surrounded by water. So we also know from the geological record that such collapses do occur and appear to actually occur quite frequently on volcanoes. So I'd like to take you to another setting now, to Hawaii. And this is the hotspot chain of Hawaii, here from the oldest to the youngest volcano, from the northwest to the southeast. And everything in gray is are the islands that stick out of the water, and the colored part is the seafloor. And we can see that the seafloor around the islands are actually littered with huge debris avalanche deposits that correspond to collapsed sectors of the volcanoes. And these are very, very big, and the tsunamis that were generated by some of these collapses must have been extreme. Of course, these are all in the geological records, so dating back several millions of years. But still, I think it's important to acknowledge that these big plane collapses happen. And we also see other evidences for past tsunamis, or in the tsunamis in the geological record. And one example is from the Cape Verde Islands. So also in the Atlantic of the west coast of Africa. And this is the island of Fogo, and you can see it's dominated by the volcano, and you can see there's a collapse scar here, and the corresponding debris avalanche on the seafloor. And what we also can see are huge boulders that once were at the seafloor and now locate about 200 meters above sea level on the opposite island. And dating showed that this was most likely transported by a tsunami caused by the collapse of the volcano on the other side here. That happened 73,000 years ago, so also in geological times. However, I would now like to make the link to what we are actually currently observing at volcanoes. And this is also a type of flank instability that is picked up by satellite-based measurements, namely GNSS or INSAR data. And we can kind of make visible by this kind of data how the onshore parts of volcanoes are sliding into the sea. And so this is an expression of instability as well, like a collapse. But of course, it's much slower. And I'm showing here three examples. So this is Kilauea in Hawaii. The very left in the center is Piton de la Fournaise. It belongs to La Réunion. And on the very right, there's Etna in South Italy in Europe. So they are all surrounded by, or they are all facing the sea. So this is indicated by basically the white part here, or the gray parts where no data appears available. And what is shown for all of them are the time averaged GNSS vectors over multiple years. And all these three volcanoes have some features in common. And that is that, first of all, their flanks all move anomalously seawards. So we can see this part of Kilauea is actually sliding seawards with quite high displacement rates, up to 8 centimeters per year. And at Piton de la Fournaise, we can also see anomalous movement towards the sea. And at Etna, we can also see this, the southeastern sector is sliding seawards as well at rates of 2 to 3 centimeters per year. So what they also have all have in common is that the largest signals, so the largest displacement signals, appear to occur near the coasts, so actually away from the summit craters. And large parts of these volcanoes are covered by water. And of course, this anomalous movement of these individual flanks does not stop at the shoreline. But we can assume, or we can almost be pretty sure that this continues underwater as well. So, however, the fact that we only have information on onshore ground deformation, that means that that offshore slip is highly unconstrained, and that results in very high uncertainties in models that seek to fit the onshore GNSS and INSAE data. So basically dislocation models that try to explain the measurements that are taken. And I have one example here from a seismic event in May 2018 from the south flank of Kilauea. So it's again Hawaii. And there was a magnitude 6.9 earthquake. And of course, the onshore GNSS stations, they did record displacement. And the slip model that fits these displacements predicts the largest slip in the offshore. So you can see here the modeled slip shows the largest slip in the offshore part where there's no data available. So there are actually no constraints either. Another example, very similar, comes from Etna, where these authors modeled GNSS data for an inflation phase. So they looked at a bit more than 1 year. And for orientation, so this is the summit, this is the coastline, and you can see the black arrows are the measured data, the red arrows are the predicted data, and they predict, and these are the slip areas that they predict. And again, they predict a huge slip up to 25 centimeters in the offshore part. And there's no data available that could validate this result. So for the next part of this talk, I would like to see how marine geophysical data can help us to better understand this sort of flank instability at coastal and ocean island volcanoes. And I'll have a particular focus on how we can better understand the structure, so the volcano-tectonic structure, the deformation of the flank, and actually the dynamics of the flank. And I will take you through several case studies where we've looked at all these three parts. So I would first of all, for the first case study, I would like to take you to Ritter Island in the Bismarck Arc. So you can see a combined onshore and offshore map here. So everything in gray is above the waterline and everything in colored again is below water. And Ritter Island is actually this little part here. So it corresponds to what we see in this image here behind the ship. It's basically a few rocks sticking out of the sea. This is the result of a flank collapse of a former conically shaped volcano. It was a 700 meter high volcano, and in 1888 this volcano collapsed and left basically these pile of rocks sandwiched in between two other islands, Saka and Umboy, in this direction. So this was actually the largest historic volcano island sector collapse, and it caused a tsunami that affected even settlements more than 700 kilometers away. So it was also a significant big event and involved about 5 cubic kilometers of material. And you can see also in this bathymetric image that the landslide that was generated extends really far, almost more than 70 kilometers away from the actual edifice. So yes, I've been talking already about this map, and this map was collected using so-called multi-beam echo sounders, and that were installed on the ship. So with this SWOS sonar mapping, we could get this this idea how the seafloor looks like away or underwater. So and this, what we can also see here is that there are a few large blocks on the seafloor. So this one, for example, so I hope you can see my mouse, this one, or this one, and this one. And these are actually large blocks that were traveling with the collapse. So they did come from the edifice and traveled not very far, but still they traveled as a whole block, so intact. And we can also see further downslope, we see some volcanic ridges that extend between the islands here. So we can also look into the seafloor. For example, one way, that would be one way to distinguish between landslide blocks and volcanic ridges. And this is done using reflection seismic techniques. So in this case, for Ritter Island, we had a 2D survey, and we also had a 3D seismic survey. And here's an image of the system and the 3D seismic system in action. And I would like to start off showing some seismic data. First of all, a 2D seismic line across the edifice. So it's this white line on the map here. And we can see quite well the collapse scars here. And we can also see, interestingly, this is the new volcanic cone. So this has been growing following the 1888 collapse. So that's the product of 150 years of volcanism, basically. So what we can also see from this image is that the edifice is relatively simple. So we have to do with well-bedded strata. And if we look at drone images that we have from the onshore edifice itself, it's probably, or the layering that we see in the seismic data is probably comparable with what we see from these images, from the drone images. So basically the interbedded sequences of scoria and thin lava. And in the next slide, I would like to show you an image from the 3D seismic cube that runs from the, so I'm going back to the image that runs from very near, from the volcanic edifice into the basin, more or less here. And again, the volcanic, so there's the non-interpreted section and the interpreted section. And on the right-hand side is, this is towards the volcano edifice. And to the left-hand side is the volcanic ridge that I pointed out on the bathymetry data. So what we can see is there are several rotated blocks. So inside this mass that we can, so this one, for example, and there is we also see folded sediments in this part, so we can see sediment folding. We also see a deep shear zone. Here is the below which we do not see any compression. And if we look at a zoom in, so it's this part, no, it's, yes, I think it's looking into this part of the strata. We do see thrust faulting, and we also see the infill changes in the folding. So we see thickened infill, and that suggests that folding and thrusting has taken place over long terms. And another thing we see is that the sediments, that the deposit actually, or this that the folded sediments are actually eroded. So we see strong signs of erosion down here, and this erosion we attribute to the actual 1888 collapse. So taking these two observations together, so evidence for compression over long terms and subsequent erosion by the actual collapse, that shows us that there were two stages of deformation. So first of all, the slow sliding of the flank on a deep shear surface, and then this was then over long terms, probably geological timescales, and then the highly energetic collapse that eroded into this folded strata. So we performed some discrete element models to just check if this is reproducible, and so I'm just showing the 3D line on the bottom again, and the very simplified model set up above, and this is what we get. So we actually get a deep shear surface. So I'm showing shear strain here. We get a deep shear surface, and we get a second shallow shear surface, which the deep one I would attribute like to this deep shear surface that we also see in the 3D seismic data, and the smaller, like the more shallow one, that would be the actual 1888 collapse. So again, bringing this information from bathymetry, seismics, and modeling together, I think we can show that Ritter Island was, like, one of its flank was sliding seawards over a long time before it transitioned into catastrophic collapse. So we saw a period of slow flat sliding of this flank, seaward sliding, and then we have the evidence for the 1888 collapse. So kind of this rings a bell again for what I've shown before, that many volcanoes nowadays actually show this slow sliding of individual flanks, this slow seaward sliding. So coming back to to this image that I showed you. So these are the three examples that I showed with slow seaward sliding flanks of these volcanoes. And I would like to take you now to Etna in Sicily, where we collected a lot of data on the structure, and where we actually were also able to show how the flank moves underwater. So this is on the left-hand side. It's a picture of Etna volcano taken from offshore. So we are actually looking on a highly populated area here at the foot of the volcano, or at this flank. So we're actually looking exactly at the unstable part, so exactly at the moving flank. We are also looking into the Valle del Bove scar. So I think it's nice, it's better shown in this relief image on the right-hand side. So this is a scar, presumably of a previous collapse that must have happened around 8,000 years ago. So as I said, we do record a flank instability. So the southeastern flank slides seawards, also depicted in the GPS vectors, showing a bit more than a year of data here. And the motion is about 2 to 3 centimeters per year. There are episodic accelerations that accompany mostly dike intrusions. And another point I would like to make is that that onshore the unstable sector is bound by fault systems. So this is this fault system, so-called Panicana fault system in the north, and a fault system in the south as well. So the flank instability is also very shows up very clearly onshore. So there are roads that are being destroyed by the slow flank movement, and we can also, again, here's a picture from a road, and the fault basically runs exactly through these gates here. So it causes a tearing apart of the gates and a subsidence of one side of the gate. And we also see, so this is the result of a crack opening in response to an earthquake. So these are all related to flank kinematics. So the flank sliding down, and again, the deformation probably or most likely does not stop at the shoreline. A large part of the volcano is covered by water, and also in this in this onshore-offshore combination on this side, we can see that the volcano does extend underwater, and that the flank is larger than just the onshore part. Again, I've pointed you to in the beginning that the displacement rates are highest at the coast, and this is also true for Etna. But unfortunately, there was little information or no information on displacement offshore from the usual satellite data. So in order to better constrain the offshore flank, we had a series of cruises there. So this is data that has been collected over over 9 years, almost 10 years now. And we do have 3 major questions. So how far does the unstable flank extend into the Ionian Sea? Then what is the magnitude of offshore flank deformation? And then what does that mean in terms of a potential hazard for a flank collapse at Etna volcano? So I would like to start with mapping and imaging. So we collected ship-based bathymetry. We also have AUV bathymetry and 2D as well as 3D seismic reflection data from this offshore part. And this allowed us to answer the first question and define the limits of the submerged unstable flank, and a little bit about the offshore structure. And for the next slides, I would like to concentrate on this southern boundary of the unstable sector. So to the north, there is the part that is active. So that's sliding downwards, and this is to the south. It's kind of the stable part. And I would like to show you just a very short seismic line across this structure. So this is the south and this is the north, and we can interpret this ridge here as this separation. We see horizontally layered reflectors in the south here, and this is not the case in the north. So there is a difference here, which we interpret as a fold. And I'm also going to show you a 3D view of a microbathymetric map of this area. So this area collected by the AUV, and we're now looking from the south. So we're looking basically from here up slope, and the data was collected with a so-called autonomous underwater vehicle that swims 50 meters above the seabed and therefore can collect this very high resolution data, which is now gridded at 2-meter grid spacing. And in this image, I think we can, it's the fold comes up quite remarkably as this almost razor sharp structure here that I highlight with the little arrows. And if maybe to some this looks somehow familiar, then this is maybe because of its similarity with a part of the San Andreas Fault in the US. So this is an aerial image of the Elkhorn Scarp segment along the San Andreas Fault that has about the same scale, not entirely identical, but very similar. And I think we can see very similar structures here of strike-slip movement. So, and yeah, in our interpretation, this is clearly the lateral boundary of the downwards sliding flank. And it is also an ideal site for a seafloor geodetic network that is capable of detecting relative seafloor deformation. So, and we have this this technique at GEOMA, at our institute, and we call it the GeoC array. It uses the so-called direct path acoustic ranging techniques. So this basically means that the distance between two monuments or two transponders on the seafloor is measured via the time of flight and the speed of sound in water. So the time of flight of sound signal being emitted from one and being received from the other. And yeah, we know the speed of sound in water, then we can calculate the distance between the two monuments. And if the distance changes, then we know the seafloor must have moved. And if we have not only two instruments, but a whole array of such instruments on the seafloor and across a fold that is related to flank movement, we can get a good idea about how the flank has moved. So an advantage of this method is that we get continuous measurements, and the downside is that we do not have information on absolute position. So this is all relative. We are also able to communicate with the network at the seafloor without having to recover it. So via an acoustic modem, we can establish an acoustic link and communicate with so we can retrieve the data without having to retrieve the whole network. At Etna, for the first deployment, we had 5 transponders available, and we put 3 on the unstable part of the flank and 2 on the stable part. They all were aligned in line of sight with each other, so we had what we call 10 baselines. So the information on the ray path between, the information on the distance between the single instruments. And they were recording for almost 2 years at an interrogation interval of 75 minutes. And coming to the data now, I would first of all like to show you a cross-fault baseline. So between these two instruments on the seafloor, and the distance between the instruments is about 804 meters. And we can see that in the first part of the deployment, the baseline was relatively stable, and until May 2017, where we see a significant reduction in distance by about 4 centimeters, and then again relatively stable measurements until the end of the observation period. So if we look at a transponder pair on the same side of the fault, just as a reference, we see there was no shortening or no change in the baseline length during this May 2017 event. And this is an artifact. This is not real. So if we, we also have information on the vertical movement from pressure sensors that are on each of the transponders. And they also indicate subsidence of these instruments relative to those. So and this is not, these are not the only baselines that show this, but it's actually, the signal is actually very consistent between all of the baselines measured. And I think, so this is putting this all together in a map view. And so overall the data is consistent with dextral strike slip motion. And overall we detect 4 centimeters over a period of 8 days. And that corresponds to, or that falls in the category of slow slip event. And this was actually the first ever measurement of strike slip motion of an offshore slow slip event. So that was also quite interesting that we were able to do that. And so we put this together with the onshore deformation in the same observation period. So mainly 3D displacements from GPS stations, and our colleagues at in Italy combined this with high precision ground displacement along the line of sight of the Sentinel-1 satellite, and what they were able to do is provide a 3D surface motion map in the same observation period. And we are now, okay, this is the INSAR information. We are now going to look just at this lower, like southeastern part. This is the surface motion map, and in the observation period. And what we can see clearly is that there are 2 main faults across which displacement has taken place in the observation period. And this is this one and this one. And we can have a look across these structures, and we can see that both of them accommodated about 2 centimeters of slip in that observation period. So this is quite interesting because 2 + 2 makes 4. So it matches well what we see offshore. And again, if we take this information from onshore and offshore together, we see that they are kinematically consistent. We also could show that offshore deformation probably is concentrating along one fault, although we only have measurements for this one fault, so we need to be a little bit careful. But it seems that this is deformation concentrates along this part. And what we can also see is that that strain appears to be partitioned if we come closer to the shoreline, and then onshore it's split up into several fault systems. So I think there are some aspects in here that has not been known before, and they both have, they do have important implications for the hazard assessment. So we could show that, I think, first of all, that the unstable flank is much larger than previously thought. So a much larger part is in motion than previously thought. And that I think we can also say that the flank movement or probably initiates offshore, because this is where we see the largest movement and the concentrated movement, and that probably there's something that pulls the flank down, which could maybe be the gravitational pull of the overall subsiding continental margin. But this is very, I think we need to confirm this a bit more. So, but I think it does show that we could improve our understanding of the processes that are driving flank instability, and I think it's a good example of why we should really also consider the offshore when we seek to understand the processes. And if we do not consider the offshore parts, then we may run the danger of misunderstanding how the system works and what its actual hazard is. So I would like to come to a brief summary of what I've been talking about. And I showed you several case studies, and I think we can say that offshore volcano tectonic structure deformation and dynamics is imageable and it's measurable. So we can both image and measure it. And that I think I could also persuade you that we need to consider the whole edifice to fully understand flank instability and what could be driving flank instability, and that there could be a link between persistent and slow flank sliding and the actual catastrophic collapse. But this is also very preliminary, and I think this is something that I personally want to try and understand a bit better in the future, how this links and if there's an actual link. And the case studies that I showed you, they are not the only ones, but they're actually a large number of also big volcanoes with slowly sliding flanks, where we don't know what the actual status or how stable the actual flank really is. So lots of things to do, but for now I would like to close this talk, not before acknowledging a lot of the people who have contributed to this work. So I listed a few of them here, but there are probably many more I forgot. And I would like to thank you for your attention, and I'm very happy to take any questions you might have.
Thank you very much, Dr. Urlau, for your very fascinating presentation about starting from getting to know different kind of volcano, underwater volcano apparently have some potential catastrophic measures in different locations around the world, including the one that nearest to us is the Anak Krakatau, which just recently collapsed in 2018. And yeah, it's a very interesting activities that you do with your research involving massive field work with the ship missions across the oceans around the world to evaluate the hazard potential of those underwater volcano and the slides that comes with it, whether it's slow onset and a very long-term geological time, and also the catastrophic ones, which is actually the one that we difficult to predict that, but it happens, just like what we had experienced in 2018 with the collapse of Anak Krakatau. So thank you very much once again for your presentation here as a keynote speaker. So I would like to welcome any questions. Maybe, I don't know whether we have time to invite for multiple sessions of the questions, but please raise your hand, I think. How do I operate this?
I have one question.
Yes,
Buela.
please go ahead, but I cannot see who's the one that...
I did raise my hand, yeah.
Yeah, sorry. Please go ahead, Pak Haikal.
Okay, thank you very much. Thank you very much, Dr. Morelia Ulau, that you have time to join our conference today. We are very sincerely thanks that you have spent a good time with us, sharing your recent work about the submarine landslide and the volcanoes. One question, at the most of the part that we couldn't do the mapping very well is located, as you said, it's located underwater. Beside volcanoes, we also have the onshore, offshore fault extensions, such as the Great Sumatra Fault Zone. We have the extension from the onshore to offshore. Palu, Koro also have extension offshore. So in time with your presentation, do you see any similar tectonic feature regarding for the activity of the faults, and then generate huge landslide, induce tsunami, or it just purely relate to the volcanic activities? Yeah, how we can distinguish between the records that we saw on the seismic section, that is from the volcanic activities, or it's from the fault extension of fault to the offshore. In our region at the northern Sumatra, we have the extension of the Sumatra fault zone to the offshore. From the seismic line, we can saw a mass transport deposit, a very thick mass transport deposit. However, we don't have any idea when this mass transport deposit occur, as well as is it resulted from the eruption of the volcano nearby, or is related to the fault activities generate this submarine landslide?
Yeah, I think that's a very tough question that I'm afraid I cannot answer. I think the problem is, so for submarine landslides in general, I think it's the research lags behind those of seismicity. So we are now starting to actually monitor them and see how they are occurring, but it's very difficult to actually say something, because all we see, like you described for Sumatra, all we see usually is the post-mortem. So so just we see it has happened, and then we can see it on the seafloor, or in the seismic data, but very, very rarely, or especially for big events, it's very difficult to say how they actually happen, and or it's almost impossible to actually monitor them, which is, I think, the kind of data that we would really need, because there's this discrepancy between we know there must have been a landslide. We can also we can use numerical models to try and understand what the conditions must have been at the time of failure, but we never know what these conditions actually were because we did not measure them at the time. So that's really tricky, and it's also really difficult because for earthquakes, you know more or less where they occur. So you have a good idea. There are fault zones, and there are earthquakes that are likely to happen at these fault zones. But this is not the case for submarine landslides. So they basically can happen anywhere in the oceans, anywhere where the slope is inclined. Yeah, so I think there's a lot of more research needed in that direction. And therefore, it's also very difficult to say anything about, I think that was also part of your question, about possible precursory signals. So how could we say that this is a signal that we should be worried about? Yeah, this is also very difficult, but I think a lot of progress is being made with the Anak Krakatau example, because it was relatively well documented in terms of data. So there was a seismic event recorded before that, but it wasn't very big. So I think how should you have known that a collapse will follow from this kind of moderate seismic event? But if you also look at other sources of information, so the temperature and the deformation, if there's I think this is the way to go, to actually look at very different kind of data and see and analyze them as a whole. But then, of course, it's always easier to say this in hindsight. So it's easier to say this now than before. So it's it's a very big challenge, and I think a lot of work is needed to actually be able to say with certainty which are critical parameters, or which interplay of different parameters could be critical.
Yeah, thank you. I have one more, not question, but we have a number of participants from the students. So do you have any encouragement for them to just how you can be as a woman scientist and then take the cruises, and then this is a very nice experience, and for the student, they saw all of your work is totally amazing. How you can give a suggestion for them, for these young students that joining this conference?
Study in Germany for sure.
Pardon?
Study in Germany, that's the first thing.
Yes, I think this is first of all, it's great that a lot of students are following. So I'm glad that that this is the case. So I guess as Dr. Mailianda said, that making experiences abroad, this is very useful, and yes, I only went across the channel to the UK, so I stayed in Europe. I didn't go very far, but still I think I learned so much just being in a different system, and also, of course, personally, but also science-wise. And so I think this is a very good thing to do. And there are a lot of schemes also out there that help for the different countries, that can help in getting a scholarship or a fellowship, for example. And in terms of being a woman, I think there's not much of a difference. And I have I have a very nice husband, and he's very, very supportive, and he's it helps that he's a scientist too, so he knows what I'm doing, and he knows that I really, really enjoy what I'm doing, and that it's important work. And so I think we share all the housework and the kids and everything. We share this very, very equally among each other. So that's it helps a lot.
Thank you, Dr. Morelia. Thank you.
So is that all, Pak Haikal? Thank you very much for your questions and also discussion about this, the later one. I have warned by the host that we have to end the session, although there should be many more questions that the audience want to address to you, Dr. Ulaub, but unfortunately we have to finalize the session, and maybe for the audience who are getting interested in understanding deeper into this volcano, landslide, underwater mechanism and everything, please have a contact to Dr. Ulaub. Is that okay, Dr. Ulaub? Of course, yeah. Yeah.
Absolutely, and I'm very sorry for running over in time.
No, it's fine. Yeah, and thank you very much for your contribution today as the keynote presenter, and we really appreciate your time and your encouragement to us also in Sheikh Kuala University to do more this kind of conferences, inviting very well-known and international researchers like you. And I would like to close the session, I guess. So thank you very much, everybody. And hope to see you somewhere, sometime in the future, Dr. Ulaub, when we probably can be returning back to traveling across the world. Yeah. Thank you very much for the host, and I will return the floor to the host. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you. Bye-bye.
Thank you, Dr. Morelia. Thank you very much.
Thank
Very nice
you,
presentation.
Dr. Morelia. Very nice
Thank you.
presentation. Thank you.
Thank you very much, Dr. Morelia Urlet, as our speaker for the last session of keynote speaker for today. So we learned a lot from your experience, your knowledge, and of course for your speech in this event. Okay, so thank you also to Dr. Ella for the lead as the moderator for this session. And I would like to say good afternoon to all of the participants. I'm so happy. I'm really appreciate we still have the highest spirits for today. And now we are in the closing ceremony session for this event. Of course, the 10th International Conference on Multidisciplinary Research, ICMR, in conjunction with the 2nd International and National Symposium on Aquatic Environment and Fisheries INSAEF 2021 for the topic for this year, all multidisciplinary approach toward a sustainable eco-blue industries 4.0. All right, without any further ado, now we will also to announce who is the winner for the 3 categories: the best poster presentation, the best oral presentation, and the best student presenter. So, ladies and gentlemen, so we'll start it now. I will announce you, this is one of the most anticipated session, and it's time for me as Master Ceremonial on behalf of the committee, will announce you for the best poster presentation goes to Muhammad Agustiar Eskel from the Institution Ocean Diving Club, Faculty of Marine and Fisheries, Sheikh Kuala University, with research project titled Community Structure of Mangrove in Lambadu. Congratulations.
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 All right, so we move to the next categories. For the best oral presentation goes to Gatut Bintoro from the Institution of the Faculty of Aquaculture, FPIK University of Brawijaya, with research project title Utilization Status and Language Relationship of Longtail Tuna, Kunis Tonggol, cooked in Indramayu waters, West Java. Okay, ladies and gentlemen, this is the last but not least for the last categories. For the best student presenter goes to Febrianto Simanjuntak. Congratulations for the institution of Center for Space and Remote Sensing Research with the research project title Depiction of Typhoon Mangkhut 2018 and its impact based on satellite observation. Congratulations for the winners for today for the 3 categories: the best poster presentation, the best oral presentation, and the best student presenter. So, ladies and gentlemen, finally, as the master of ceremony, on behalf of the committee, I would like to say thank you very much for all of the participation, keynote speaker, and also all of the committee for the best in order to successful in this conference. See you on the next event, the 11th International Conference on Multidisciplinary Research ICMR. Assalamualaikum warahmatullahi wabarakatuh. See you and have a good afternoon to all of you. Bye-bye.
See you. Bye-bye. Thank you.
Bye-bye. Thank you very
Thank you,
much.
everyone.
Thank you.
See you again.
Bye-bye.
Yeah.
Thank
Bye-bye.
you.
Thank you.
Thank you, Toyo. Toyo An. Hi.
Thank you, Dr. Dohai.
See
Thank
you again in
you.
the next year. See you.
Bye,
Thank
everyone.
you. Bye-bye, everyone. Thank you.
Thank you.